Namaskaram. In this session, we will see a special decomposition of an M-by-N matrix that is called singular value decomposition. Let A be an M-by-N matrix with rank R, then there exists an M-by-M orthogonal matrix U and M-by-N matrix sigma. So sigma is an M-by-N matrix and an N-by-N orthogonal matrix V such that A can be written as U sigma V transpose. And this decomposition is called singular value decomposition. Okay, then how to find this how to find the sigma? Sigma is very easy. First we have to identify the singular values of A. What are the singular values of A? Yes, we know that singular values of a matrix A is the square root of the eigenvalues of A transpose A. Okay, and we normally write in descending order, decreasing order. Okay. Okay, so we arrange that singular values in decreasing order. Also, there is a result. Since the rank of this matrix is R, there are only R non-zero singular values. Remaining n minus R singular values are 0. Okay, so for a matrix of rank R, it has only R non-zero singular values. So we arrange that non-zero singular values diagonally. That means actually this is a submatrix. We can view this as a submatrix with the order R by R. Okay, what is R? R is the rank of the matrix, or R is the number of non-zero singular values of A. Okay, both are same. Then actually, what is the order of sigma? Order of sigma is m by n. So its order is m by n. So if this matrix is not m by n, then we have to add as many as zeros such that the new matrix is m by n. Clear? Actually, here we add sufficient number of zeros for making the whole matrix is m by n. If it is not m by n, okay. Okay, next one is the construction of V. How to construct V? V is a matrix like this: V1, V2, etc. Vn. Actually, here this V1 is the first column of V. V2 is the second column of V, like that. Okay, Vn is the nth column of this V. Then how to find V1, V2, Vn? Where V1, V2, Vn is an orthonormal eigenvectors of A transpose A, corresponding to the eigenvalues lambda 1, lambda 2, lambda n. Okay, so actually already we discussed this problem in previous session. In this session, we will find the singular values of this matrix and corresponding orthonormal eigenvectors. And these eigenvectors are orthonormal. That means their norms are 1 and mutually perpendicular or mutually orthogonal. And they are the eigenvectors. They are the eigenvectors of this eigenvalue. That means this eigenvector corresponding to 360 and this eigenvector corresponding to 90 and this eigenvector corresponding to 0. Okay. And one more thing, here we assume that lambda I is also in decreasing order. Okay. Okay, last part is U. Then how to define U? Okay, U is a matrix like this: U1, U2, etc. Um. Because the order of U is m by m. Okay, m columns and m rows. Then what about ui's? Here, this is actually I is varying from 1 to r. That means you can find u1, u2 up to ur using this formula. What is the formula of u1? u1 is 1 by sigma 1 into ab1. Clear? And what is u2? 1 by sigma 2 into av2, like that. Okay, this is possible only for non-zero, corresponding to non-zero eigenvalues. Okay, so sometimes this r equal to m, then no problem, we have sufficient number of ui's. Suppose r is less than m, then it is clear that this u1, u2, etc. ur is somewhere here. We have to find remaining m minus r vectors. How to find this m minus r vectors? If r equal to m, there is no issue. U is given by this u1, u2, ur, no problem. Otherwise, we have to add extra m minus r vectors. What is the rule of adding this m minus r vectors? This is the rule, where u1, u2, etc. um is an extended orthonormal basis for rm from u1, u2, ur. because already we have u1, u2, ur, no doubt, because we have r non-zero eigenvalues corresponding to r non-zero eigenvalues. We can define this one. Okay, if r is not equal to m, so we have to extend that set to a basis for rm by adding remaining m minus r vectors. So that basis should be orthonormal. That means these vectors are orthonormal. Theoretically, this is possible. Okay, so this is the construction of U. Okay, consider a problem. Find the singular value decomposed of this matrix. You can take this as A. What is the order of this A? 2 by 3. Okay. Okay, in last session, we have seen that how to evaluate the singular values and corresponding orthonormal eigenvectors of A transpose A. We know that the singular values of this matrix are eigenvalues of A transpose A, and eigenvalues of A transpose A are 360, 90, and 0. And we choose lambda 1 as uh, uh, biggest one, choose lambda 1, and we take in a decreasing order. So this is lambda 2, this is lambda 3. And you take the positive square root, that is sigma 1. So sigma 1 is positive square root of 360, and sigma 2 equal to positive square root of 90, and sigma 3 equal to square root of 0, that is 0. So these are the singular values. Also, we know how to evaluate the orthonormal eigenvectors. What is the rule? First, we find the eigenvectors corresponding to 360. Let me suppose W1, W2, W3 are the three eigenvectors corresponding to 360, 90, and 0 respectively. Then we define V1 as W1 by norm of W1. This is a unit vector. Already A transpose A is symmetric, so their eigenvectors corresponding to different eigenvalues are a property. They are mutually orthogonal. So we don't bother about that part. That part is automatic. So we have to, only job is we have to normalize this W1, W2, W3. They are automatically orthogonal. Okay. So by normalization rule is we divide with its norm. So V2 is defined by W2 by norm W2, etc. like that. So this is our V1, this is our V2, this is our V3. Okay, so now sigma and V are clear. What is sigma? Okay, sigma is an m by n matrix. Okay, order of sigma is same as order of the given matrix. And V is clear. You simply arrange V1, V2, V3 as columns of matrix. That is our V. Okay. Okay, so first entry is sigma 1, that is 6 root 10, and the second entry is sigma 2, that is 3 root 10. Okay, and we know that order of sigma is same as order of this one. So order of sigma should be 2 by 3. So we have to add sufficient number of zeros, making this as a 2 by 3 matrix. So we add a 0 here, 0 here. Now it is 2 by 2. To make it 2 by 3, add 2 more zeros. Now this is our sigma. Clear? So sigma is clear. And similarly, what is V? V is nothing. You just arrange V1, V2, V3 as columns. That means 1 by 3, 2 by 3, 2 by 3. Second column is minus 2 by 3. So this is our V. So sigma and V are clear. So next we have to construct our U. What is U? Okay, ui's are given by this formula. Already we have two non-zero and new singular values, two non-zero singular values. So corresponding to these two non-zero singular values, we can write u1 and u2. And what is u1? u1 is 1 by sigma 1 into av1, and similarly u2 equal to 1 by sigma 2 into av2. Okay, so what is u1? u1 is 1 by sigma 1, sigma 1 is 1 by 6 root 10 into av1. A is here 4, 8, 11, 7, 14 minus 2. This is our A into v1. This is our v1. v1 is 1 by 3, 2 by 3, 2 by 3. Clear? So this is our u1. Similarly, you can evaluate u2. Okay, so similarly u2 equal to 1 by sigma 2 av2. Here sigma 2 is 3 root 10. So this is our A. A means 4, 11, 14, 8, 7 minus 2 into v2. This is our v2. Okay. Upon simplification, u1 is like this. Upon simplification, this become 1 by root 10 minus 3 by root 10. Now u1 and u2 is there. The next question, what is the size of this u? What is the order of u? Yes. In our result, there exists a m by m orthogonal matrix U. The size of U should be m by m. What is m? M is the number of rows of A. Okay. Okay. So in this case, what is the number of order of this A? Sorry, number of rows of A. This is 2 by 3 matrix. So number of rows is 2. So it is clear that U should be 2 by 2. This is very important. U should be 2 by 2. So no need to extend this UIs because already we have two vectors. So U is very clear. You simply write U1 and U2 as a columns. Then this is our U. Okay. No need to extend. But suppose U is suppose 3 by 3 like that. Then we have to extend. Clear? Okay. So U is equal to 3 by root 10, 1 by root 10, 1 by root 10 minus 3 by root 10. Okay, so now everything is clear. U sigma V. Now you can write the singular value decomposition of this matrix. Okay, so this is the singular value decomposition U sigma V transpose. Actually, this is minus. There is a typo. Actually, this is a minus 1 by 3. Typing error. Okay. Anyway, this is our U. This is our sigma. This is our V transpose. Okay, transpose of V. V is V1, V2, V3. This is a transpose. So this is a singular value decomposition. Okay, consider one more problem. Find the singular value decomposition of this matrix. Okay, so this is our A. So what is our first procedure? First step is find A transpose A, then evaluate the eigen values and assume that what is the order of A transpose A? Yes, here A transpose A is 2 by 2 matrix, and A transpose A is okay. This is our A transpose A, and then find the eigenvalues. And these are the eigenvalues 18 and 0. 18 and 0 are the eigenvalues of this matrix. Okay. So what are the singular values? Yes, this is root 18 and this is 0. So these are the singular values. So it has only one non-zero singular value. So here R equal to 1. That's true because rank of this matrix is also 1. Okay. Then what is the next step? Next step is we have to find V1 and V2 and orthonormal eigenvectors of A transpose A. Okay, then what is the algorithm for finding V1? First, you have to find an eigenvector corresponding to lambda 1. Let it be W1. Similarly, you can find a eigenvector corresponding to lambda 2. Let it be W2. Then what is V1? V1 is W1 by norm of W1. Okay. Similarly, you can find V2 is equal to W2 by norm of W2. Okay. Then okay, to find this W1, you have to solve a minus 18I x is equal to 0. Okay, by solving this equation, you have to find all the eigenvectors corresponding to 18. Then pick any one of them. That's all. That is our W1. Then you can create V1. Similarly, V2. For this example, V1 is like this 1 by root 2 minus 1 by root 2 and V2 is equal to 1 by root 2, 1 by root 2. Okay. Yes. So these are the singular values of this matrix and these are the orthonormal eigenvectors corresponding to the eigenvalues 18 and 0. Okay. Okay, now we are ready to write our sigma. What is sigma? What is order of sigma? That is order of given matrix. That means 3 by 2. Okay, then how to construct sigma? First, you have to write all the non-zero singular values diagonally. We have only one non-zero singular value, 3 root 2. So, you write 3 root 2. Then next we have to make this matrix as 3 by 2 matrix by adding sufficient number of zeros. Clear? So, what is sigma? Sigma equal to 3 root 2, 0, 0, 0, 0, 0. Now, this is our sigma. Also, you can write V. What is our V? V is nothing, just arrange this V1, V2 as columns. That means 1 by root 2. So, sigma and V is ready. So, now our only headache is to find which one our U. Then what is the construction of U? Okay, before that, what is the order of U? Order of U is M by M. M is the number of rows of given matrix. Okay, so in this case, our M equal to 3. Number of rows is 3. So our U should be 3 by 3. Clear? But this formula is applicable only for non-zero singular values. We have only one non-zero singular value. So you can find u1 using this formula. The remaining u2 and u3, you can evaluate this u2 and u3 using this rule. That means you have to extend this u1 as u1, u2, u3 such a way that the new set is orthonormal basis for Rm. Here m is 3. Okay, that's idea. Okay, so our u is 3 by 3. It is of the form some u1, u2, u3. They are the columns of this u. And you can find this u1 using this non-zero singular value. That is u1 is given by 1 by sigma 1 into av1. That is 1 by 3 root 2 into, this is our a, this is our v1, this is our v1. Upon simplification, this become, okay, so this become 1 by 3 minus 2 by 3, 2 by 3. So first column is ready. So next we have to find u2 and u3. And what is the property of the set u1, u2, u3? This set is orthonormal basis of R3. Okay, so this u2 and u3 both are orthogonal to u1 and all of them are unit vectors. That is the idea. Okay, so suppose x represents u2 and u3, then it is clear that this u1 is perpendicular to x. That means inner product of u1 and x equal to 0. X may be u2 or u3, whatever be. Both are orthogonal to u1. Okay. So if you take x as, okay, if you take x as x1, x2, x3, already what is our u1? u1 is 1 by 3 minus 2 by 3, 2 by 3. Then what is inner product of u1 and x? We know the inner product of u1 and x is defined like u1 transpose x. If you take the transpose of this vector and you consider u1 transpose x, that is equal to 0. So that means 1 by 3 into x1 plus minus 2 by 3 into x2 plus 2 by 3 into x3 equal to 0. Okay, so this become, okay, 1 by 3 into x1 plus 2 by 3 into x2 plus 2 by 3 into x3 equal to 0. And 3 is common, you can take outside and cancel. So this equation become, okay, x1 minus 2x2 plus 2x3 equal to 0. That means if a vector x is orthogonal to u1 means that x should satisfy this equation. So by solving this equation, you can find x1, x2 and x3. Okay, you can easily solve this equation because this contains only one equation and three arbitrary variables. Three unknowns, sorry. So here n equal to 3 and the rank of the system is 1. Okay, so you can substitute n minus are arbitrary. So in this case 3 minus 1, that's equal to 2 arbitrary. Okay, I am going to choose x2 and x3 are arbitrary for solving the system. Okay, so I'm going to choose x2 equal to a and x3 equal to b. So x1 is 2a minus 2b. Okay, so you can write general vector x which is orthogonal to u1. Okay, so 2a minus 2b, a, b. You can choose any arbitrary number for a and b. So I'm going to create two independent vectors from this one by choosing a equal to 1 and b equal to 0. This give one vector, that is u2, and another vector is given by a equal to 0 and b equal to 1. So let it be some, okay, actually this u1, u2, u3 are orthonormal. That means orthogonal and unit. Okay, this substitution may not gives normal vector. Okay, the guarantee is that they are orthogonal. Okay, so I am going to put this as w2. What is w2? When a equal to 1 and b equal to 0, this become 2, 1, 0, right? And similarly, we denote the second one by w3. Okay, the guarantee is that these vectors are orthogonal to u1. Okay, because we solve the system inner product of u1 x equal to 0. So they are orthogonal to u1. Okay, so but this w2 and w3 are not mutually orthogonal, need not be orthogonal, but they are linearly independent. This set is linearly independent because we choose w2 and w3 such a way that, okay, so they are linearly independent. We know how to construct an orthonormal set from a linearly independent set. That is our Gram-Schmidt orthonormalization process. So next we apply Gram-Schmidt orthonormalization process to the set W2 and W3. Okay, that gives a new set of vectors which are orthonormal. That is our U2 and U3. Clear? So next we apply the Gram-Schmidt orthonormal process on this W2 and W3. That gives U2 and U3. So the by applying Gram-Schmidt orthonormal process on W2 and W3, U2 is like this. So U2 equal to 2 by root 5, 1 by root 5, 0, and U3 equal to minus 2 by root 45, 4 by root 45, and 5 by root 45. Now we are ready to write our U. Okay, U1 is already available. So you write U1, and this is our U2, and this is our U3. Now everything is clear. U, sigma, and V. So you can write the singular value decomposition of this matrix. Okay. Okay, this is the method of extending a R element set to M element set such a way that the new set, this U1, U2, U3 form a orthonormal basis for R3. Actually, this columns of U forms a orthonormal basis for R3. Okay. Yes, so this is the singular value decomposition. This is our U, this is our sigma, this is our V transpose. Okay. Okay, thank you.